security. So we put this NT 3.51, trying to get an internet provider, and we start to host controversial material. It was not child pornography, it was political material. So we start to suffer all these kind of attacks from everywhere, spams, denial of service, and etc. So I learned from the experience. I consider myself a person who has learned from the experience of the security. At the same time, I was studying at university, and I find out that a nice way to get a job is to find a place where you can do your hobby and they pay for you. So I started in Spain to do research. They pay me badly. I work 14 hours a day, and I started to research about this kind of topics. And after 1 year or so, I find out that it was quite complicated to research about this, because you are considered to be pro-terrorist, or anonymity looks like something like weird. Now they call it protection of personal privacy. So depending on the place I go, I talk about protection of personal privacy or personal identifiable information. If I come to a place like this, I would probably talk about anonymity. Just the word anonymity, sounds like only for bad things. So I moved to Sweden after spending some time in the jungle, in the Amazonia, building radio links there. And I discovered that radio is a nice thing because, provides you the possibility of expanding the network. And you have here this network up and running that proves that, that we can build it fast, low cost, and probably untraceable if we use the right tools. So I started my research about mobility internet, trying to find out how it's going to be the future and which privacy concerns are going to be around in this called mobile internet. For the experiments in Sweden, I built a network for the students. There were 250 students at university. They carry one laptop like this one in Kista, in Stockholm. We build this wireless network, and while we build the wireless network, we emulate what Big Brother will do in the future with the wireless internet. So I built a monitor system called the Big Brother system at university, trying to, to show to the people the problem. So my objective today is try to explain you what is the problem with mobile internet. I mean, what is the privacy problems around mobile internet, and how IPv6, is going to really help a lot of people to track devices and probably track you. My agenda for today is I will explain. We have 20 minutes, so I give a seminar of 4 days about this. So this is going to be extremely compressed. So all of you that are hardcore techies, forgive me about my short assumptions about the things, and I will explain this to get some speed. Really, it's going to be a big overview. So I want to explain what people consider security. I'm going to talk about mobility and security. I'm going to state that what is the problem that I try to solve. Some of the things that that we have deployed to solve the problem of location tracking. And I'm going to explain you. I'm going to give you here in the last part 24 studies about this network, so you can get a real picture. What's going on here in the wireless, and what an operator can know from you just in 24 hours. So we're going to go to in the final part of the presentation, we're going to see some nice figures. So when we talk about secure communications, the typical things that all people talk about is integrity, authentication, and confidentiality. What that means is, when Alice is talking to Bob, this Alice and Bob, can be two neighbors talking by the phone. It doesn't mean, it has nothing to do with IP networks or computer networks. Alice wants to make sure that Bob is Bob. Alice wants to make sure that the message that Bob is delivering, is the right message. And Alice probably no one to read the message. That's the typical 3 attributes, we want in any kind of secure communication. In IP networks, that looks like this, An IP packet, I really hate to do this. An IP packet looks like, this is a big simplification, but an IP packet basically looks like a header where it says from and to, and a payload where is the message. This IP packet, looks very similar to whatever message, a letter from Alice to Bob and the message. So when you send an envelope from one place to another, you're doing the same process. You put the from, and probably you put the from in the letter, and the destination, you put the payload inside. IP packets have the same kind of properties, IP packets carry the from and the destination. So our man in the middle, by watching that IP packet passing by the network, can figure out a lot of things. This is a IPv4 IP packet. So a man in the middle, by watching this packet, knows that this IP address is talking with this IP address and is sending this message. This is an ICMP packet that, if the message is encrypted, anyway, a person in the middle can see that IPA is talking with IPv, and they're using these MAC addresses in the link level, if that person is in the link level. What I'm trying to say is that you can build a system extremely secure in the content of the message. You can build a system nobody can break and nobody can read the message, but the information that Alice is talking to Bob is in the headers. So there's an information there that the 2 persons are communicating that, a standard mechanism of crypto is not protecting. The IP itself needs the headers to route packets. So my focus is about, the arrow, that thing here, the arrow. So I'm interested about the arrow. The Alice is talking to Bob. And you will say, oh, that's not information. I told you today, with the amount of information that is passing through the network, and the government is interested in tapering lines, that's enough. That's enough. If Alice is, I will say, put the example, if Alice loves pancakes, and has a pancakes organization, because they have a computer club and a pancakes organization, and Alice sends mails to the people saying, oh, are you interested in pancakes? A man in the middle can read the message and know about that, but by just watching, where the packets are going, you will be able to know who are the people talking with Alice and create these community groups of people of interest. And that kind of information is extremely useful, especially, with mobile internet. So you get the point that the problem is not the message itself, it's the headers of the packets. So 20 seconds on mobile IP version 4. In mobile IP is a protocol that tries to solve this problem. If I take this computer with me and I move to Spain, obviously I had to get a new IP address. I know you understand that. So every time I move to another network, I had to get a new IP address to communicate. So if I'm in a mobile internet where there's a lot of radio cells around, and those radio cells are different IP networks, if I'm moving, every time I move, I have to get a new IP address, and all the TCP connections, UDP connections are broken, and I have to restart again. A typical example, with Windows, you come with Windows 98 to a network, you have to get a new IP address, fix the new IP address, and reboot. So what mobile IP is trying to solve is that it doesn't matter which IP address you have, someone will deliver the packet to you. So when Alice is talking to Bob, if Bob is in the home network, that's fine. You get the packet and you read it. But if you move away, you move somewhere in another country, in another radio cell, this place called home network will tunnel the packet to you, to your new destination. So mobile IP handles all this signaling and registration, into the network. When you say, okay, now I'm here, send me the packet to Spain. Now I'm in Sweden, send me the packet to Sweden. Now I'm back home, you don't have to send the packets anyway. So in the home network, let's say this is my computer at home in Sweden. There is something called home agent that will grab the packets from the network and tunnel them to your destination. This is very useful for keeping the IP fixed while you move, but has an obvious problem, and is that, if someone wants to talk with Bob, let's say Alice, and Alice is in the same country, let's say that Alice and Bob are in Sweden, but Bob is from Spain, the packets go to Spain and forth to Sweden, despite that both are in the same country. And why? Because Alice doesn't know that you are in the same country. Only the home network knows where you are. So that's called triangle routing, and the problem is that the packets always have to go to the home network and be delivered where you are. So your home network is extremely far away, let's say in another continent. You are a member of American University and you move to Europe. The packets has to go back and forth through, through the Atlantic just to get into just to know it's communicating in the same country. So the people from IPv4, find out that IPv4 itself cannot solve this problem. You need a mechanism that when you are abroad, you tell to Alice, I'm not there anymore, please send me the packets straight away. In IPv4, they call it route optimizations, and there's some extension for IPv4, but all those things have been moved to IPv6. So in IPv6, you will have something like this. When Alice is talking to Bob, and if Bob is at home, that's the normal communication that you use. One computer is talking with another. If Bob moves away, the package of Alice goes to home network. The home network delivers the package to your foreign network, your roaming network. And then Bob can make a decision. Bob can make a decision if I want to tell Alice where I am. Okay? If Bob tells to Alice where I am, he's providing location information to Alice. I'm here in this moment. So as you see, if you want to get routing optimization, if you want to make fast routing, you have to tell to the people you're talking with where you are. So in IPv6, the possibility of building this Alice to Bob straight communication is called binding updates mechanisms, and those mechanisms allow, to your correspondent nodes, the people are talking to you, to know where you are. And why this is good? This is extremely good for fast routing when you're moving around. But it's extremely bad in terms of privacy. Someone can just ask you all the time, where are you now, where are you now, where are you now? Of course, you are supposed to have the possibility not to say where you are. But as we know, the things want to be efficient in the routing and not in the privacy. I mean, people are not willing to wait 10 seconds more to encrypt an email, where they're going to wait, 400 milliseconds more to get their package delivered home and back in terms of protection of privacy. So what is going to happen, and that's what is going to happen, is that all the devices will implement route optimization with IPv6. All the devices by default will say where they are. So, we'll have extremely voice over IP over IPv6, extremely fast handovers, all these kind of things. But we will be monitored by the people. This is another more idea for what happens in IPv6 addresses. As you know, in IPv6, you're going to have 120 bits. We're going to have so million addresses for everyone that everyone is going to be extremely happy. So each one is going to have their bunch of networks to work. But the guys that designed the IPv6 decided something extremely interesting. They say, okay, we want to get rid of DSTP. We want to make these IPv6 devices so smart that when you just put them there on the floor and you're switching them on, it will find out, which IP address they have, in which network they are, and that's all. That's called IPv6 stateless address configuration, and it's a mechanism by an IPv6 device gets an IPv6, unique IPv6 in the network without the need of a DSTP. So that IP address is done in this way. The 64 bits to the right, depend on your MAC address. I will explain that how it's built. And the other 64 bits, you get them for the advertisements of the router. So the router is saying, this is my prefix, this 64 bits correspond to my network, and you generate the other 64 based on your MAC address, and you get the 128 bits. How that address is built is configured in this way. This is, for example, that one at the top here, that's my MAC address. This is my WebLAN MAC address. It's an IEEE 102.
this is 48 bits. That's the MAC address of Ethernet. You just put another 16 bits here. You always put FFFE. I'm going to make this very fast. There's a reason for this. So suddenly from 48 bits, they are supposed to be unique. The MAC address is supposed to be unique. You put another 16 bits here. And then it's a kind of swapping bit here. It's a kind of universal local bit. But anyway, you can assume that you just swap one bit here from 0 to 1. And at the end, this is going to be what is called interface identifier. In Ethernet, your 64 bits, will create your 48 bits of your MAC address will create a 64 unique interface identifier that will look like this. So with this 64 bits plus the prefix of the networks that they are at the top, you build these 128 bits. So what is the problem with this? That if you move to another country, the 64 bits in the right would be always the same. So it doesn't matter where you are, the 64 bits that you have in your address will be fixed. So you move around with this magic way of configuring your device, and by watching the 64 bits and correlating that, someone can know where you're moving around. So someone in the IPF said, oh, this is very dangerous for privacy. We'll have to do something about it. There is a draft to solve this problem and say, okay, instead of getting the 64 bits based on your MAC address, the people have concerns, let's create a random 64 bits. So every device, that wants to have lots of privacy will create 64 random bits, and we'll try to find out if someone else in the media has those 64 random bits. That's called duplicated address detection mechanisms. That if someone else has these 64 bits, then I create another 64 random bits. Sounds quite okay. And every time you move around, you create another 64 bits for your MAC address. So in the discussions we have, I say, I don't like that. And why I don't like that? Can you figure out why I don't like that the 64 bits are random? Why you think that having 64 random bits will really be a kind of protection of privacy that's a bit fake? Because, the MAC addresses in the world, they are not random. You know that 0061D is Lucent. That's a Wetland company name. You know that in the 48 bits that you have in a normal MAC address, that one at the top, the first 24 bits correspond to the company unique identifier. So in your MAC address, you have 24 bits that depends on your brand of your device, another 24 bits that are generated by the company for all the devices. So if we generate a 64 bits random in the network, we will have this kind of IPs. We have people that don't want to use the privacy extension, that are using, let's say, Lucent or the most common device, and all of them look like very nicely made IPs, and we will have another group of people that have concerns about privacy, and that will generate the random bits. So how nice for privacy? People generate random, because the problem is if everyone in the world generates random bits, then it's wonderful. But no, this is a privacy extension. And what by privacy extension means that the people that want to have privacy will create a IP in this way. So our friend in the middle, Charlie, the only thing that has to do is to find out what are those people that are interested in privacy, and try to see what they're sending. Extremely useful for tapping devices, where they have only to look for weird 64 bits in the network. So in order to prove that, I've been making some statistics here in the network. I'm going to go back to this. This is our HAL network. So you get an idea that how random is the MAC addresses in the world. 81% of the MAC addresses of the wireless nodes, we have 458 wireless users in this network now. 459, I think, my last measurement. So 81% of those people are using Lucent devices. So people from the, from marketing are very interested about this study, because this 81%, and you have 60% of those, the 60% of the total are the New Orinoco's ones, and these are the wavelengths. And then we have 8% of Mac, probably Apple users of iBooks. And then we have the rest. So you say that 81 plus 8% makes 89%. We have 89% basically there. So what will happen if I'm a very cool guy? I will have someone probably here that creates this IP for privacy concerns. This MAC address was in the network. There were only 3 people that create a MAC address random. You know, they wanted to be so anonymous, you know, that they create this random MAC. So what happened? I identified them in the network. And let's say that I communication to see what they were doing. So as you see, 3 people for 358 in this network. We don't know them personally. They find out that they don't want to have a typical MAC address, and they change it. How cool I am, and changing my MAC address with the Windows. And they create this 1234, 1234, 5678. I think it's missing 1234 again. So, you see, people randomize MACs. People create MAC addresses thinking they're going to protect their privacy in IPv6. What is going to happen? Those people are going to be out of the crowd, and they're going to be monitored. That's what I think is going to happen. So my suggestion, my proposal, you know, for getting a bit more of improvement in the IPv6 privacy is that you should not create a random IP, 64 IP. You should create a randomly, you know, statistically normal IP address for the link media you have. And then probably the people from mobility will say, oh, that will take lots of time because you have to learn. I mean, you have to learn which kind of MAC addresses are in the media to get one that is something like that. So a possibility is that the router is saying, you know, in this media, we have 81% of lucent cards for your information. So you will create a 64 bits from a lucent card. You understand the point? Probably, you know, this proposal will never get through ITF, because then it sounds very weird that the routers, for privacy concerns, they're going to advertise the statistical average of brands in the network. But if we talk about telephony or all kind of systems, maybe this can make sense because the random, there's not going to be so much randomness in the GSM devices that you're going to have. So let's go back. So one thing I want to remark is that in IPv6, the 64 bits on the right will be basically fixed all the time. And while you move from the network, someone can correlate that information and know where have you been moving around. So our man in the middle, the only thing that has to do is to be extremely close to your home network, tap your home network, where you are supposed to be, and see all those packets going out to your home network and see where they're going. Collect all these destination IPv6 addresses and know how you're moving around. So it would be extremely easy just to know how people move. So the goal, when I start with this, is how is possible that I can move and I can roam in a foreign network where my home network doesn't know where I'm roaming, and my foreign network doesn't know what is my home network, and the correspondent node that has no idea where I am, and anyway we can communicate. That sounds like weird. How is possible to destroy IP? Because at the end, all this passed by, let's destroy IP. You know, I'm going to be in the network, no one is going to know where I am, and I'm going to pay for that. I'm going to pay to get access. It's supposed to be also accountability, because one of the things that people say is, okay, this is very funny, we can put this, but how will we make the people pay? If we don't know where they are, we don't know, you know, which home network they belong, how we charge them. So, based in well-known technologies to hide the final destination, probably you know about remailers. You send the basic idea about mixes remailers is that you send a message in a multi-layer envelope where each of the routers of the network only know the previous and next hop. So if you need really to know where is the final destination, you need to get information from all the routers at the same time. So based on that core technology, I started a research project with Zero Knowledge in Canada to try to improve Freedom Network. That's their commercial product for this, to extend mobility. The challenges are a lot. You are supposed to be able to, I'm going to show you this picture. Let's say that you are this guy there in the small radio cell, and then you hand over to this big radio cell. This is called vertical handover. And in practical life, this means I have my Lucent device, I'm inside of this building, I go out of the road, and instead of being a waveLAN, you have GPRS or you have UMTS, we'll see it one day, and then I'm supposed to be able to keep communicating when I move out, okay? So we're going to have different kind of radio technologies around. One kind of radio technology is going to be indoors, and one kind of radio technology is going to cover outdoors. And I would like to go from one to another, keeping the connection active and hiding my location. So based on that idea, I'm not going to get into the detail of the protocol. I bring some, if you want to spend some time reading, I bring some copies of my thesis about this. It's full of IP stuff. And you can get a copy because I don't want to come back to Sweden with them. So if you're interested, you can get one. But the basic idea is that I'm supposed to be able to rebuild this telescope route in Freedom from here to here without revealing to the exit node that I'm doing that. In other ways, you have this cloud that's internet. You know, you start to talk by one point of the cloud. Your traffic flows out by another point in the cloud. And then now I change my input point in the cloud, I move somewhere else, and the output point in the cloud has no idea that I'm moving. So that's the goal here. The goal is that the exit node, where the traffic is flowing to the world, where the proxy is flowing to the world, has no idea about my mobility. I'm hiding, you know, to the exit point, my input point in the internet. And I have this kind of they call the people from the Army, from the Navy, they call them onion routers. The people from Zero Knowledge, they call them anonymous internet proxies. I have this kind of routers, special routers in the network. They're going to make the job in the middle. As you probably know, this system, in terms of performance, in terms of quality of service, you know, in terms of what you expect from internet, is not the best. I mean, suddenly, you know, you're passing by 3 routers with 3 encryptions, 4 encryptions in this case. You know, these kind of things are extremely expensive for the protocol. So what is the final result? The final result is that we have an IP protocol. We have these kind of internet protocols that when they are designed, in the drafts, always at the end they write this sentence like security and privacy. You know, so you see the agenda of all the groups. In this agenda, you always find these 2 lines that says security and privacy, and in that order. First, we fix the security, and then the privacy. So when you design a protocol when you put in the agenda the security and privacy at the end, what you end up doing is that it's so difficult to solve. I mean, it's so difficult to put privacy in IPv6 without just screwing up the whole mess again. And so we're going to end up, you know, forwarding packets using destination options to another part of the world and coming back. And of course, the people are going to use this kind of technologies, you know, they will be very obviously out of the crowd and will be traceable. You cannot hide that they are there. People will know that you're trying to prevent it. So IPv6 helps a lot for mobility, but it's going to be extremely complicated to implement a real privacy extension into that. So some data from the network. This is the data we've been collecting. That's from yesterday until 16 hours. This is the growth rate of the MAC addresses in the network. We can measure here how many people are coming to the network. You can see clearly that, you know, we grow fast in the middle from 4 in the morning until 2, 3 o'clock. They have a race, and now we are getting flat. I don't think we are going to reach 500 users. Making studies about the MAC addresses, you have seen this. 81% of the MAC addresses are Lucent.
So what is the point of this? Mobile friends. Let's say that we implement a system in HAL that is able to monitor in which radio cell you are. Let's say that we do that, and we collect, every MAC address where it has been moving around. And I insert that in a huge database where I have 458 users and the places they have been in the time they have been. Let's say that I pick 2 random users on the network and I paint where they have been in the time. As you see, these users in this scale, in the Y scale, have different access points identifiers, and here I have time. As you see, these 2 users, they have been moving around and they haven't really been much time in the same radio cell. Probably they pass by here for a while. But let's take another 2 random users from the network and monitor their position in the network. As you see, these 2 users look like, they've been together from this time of the day. Okay, this is 24 hours. Yeah. So if in 24 hours you get this, if I collect data for a month, I promise you that I know who is your friend, who you move with, where you go, and who you're talking with all the time. And this can be done by operators. With IPv6, it's going to be so easy to do that. So you think they're not going to do it? Of course they're going to do it. They're going to do it, and they're going to sell it. And they're going to steal your privacy first, and they're going to say, first I steal your privacy, and then I'm going to sell you the privacy extension. So first, they steal this data from you, and then if you want to be private, they have to pay something there, so we don't sell the data, or God knows what's going to happen with this. Yeah. Yeah, they're doing this with cell phones, of course. The problem is that you have to see only for this network in 24 hours we have 8 megabytes of data. Just positioning data. You have to imagine that this mobile telephone is a lot of data, you have to move it and correlate it. But it could be done. I think it's done. So just a example, we have 3 minutes more. This is myself, I choose myself from the network. This is what I've been doing in the last 1 day. You can see all the 4 correspond to a small big 10, 12 to big 10. This is the position of the access points, and this is where I've been moving around. So this is my own tracking. So if the traffic operators, they will be able to know where you are by watching the link label. And your correspondent node will be able to know how you move from outside. My final conclusion says that mobility, optimization, all these kind of things are going to be very difficult to solve against privacy. If you want to have a wonderful internet connection, full speed, you will have a lot of synchronization in the network. So the IPv6 mobility features help a lot to the tracking. They're going to help a lot to provide location-based services. And another conclusion I want to say here that I have for HAL is that I really believe that a nice privacy extension will be to create a pseudo-random IPv6 address. And if some of you are working in the ITF, I would like really to submit a draft there and push that and make some lobbying to get that in the IPv6 spec. And then once again, for location privacy, we will end up doing mixes, proxies, and we will have models like anonymizer or freedom. So we will end up again not using the feature of IPv6 and screwing up everything again because we cannot really do much with IPv6 in terms of protection, location privacy. The protocol itself is built for another thing. So I think the users that we want privacy, we will end up having this kind of awful internet connection that breaks because the proxies they're not working or the remailers are not delivering or these kind of things. So I think that's all. If you have some questions, I think we can get at least a couple of them.
Yeah, what about if you change the 64 bits related to the MAC address at certain times. So basically every 2 hours, every 4 hours. What's the behavior when you do that? Does that result in more connectivity time or longer time to connect?
I think that my suggestion what you should do is you should use, and the question is, because I have to, the question is, what happens if how long I have to change this, then I understand that these bits to get privacy. And my suggestion is you should have different kind of random bits for different kind of profiles. So when you want to be, it's basically of names. You want to be this person with this prefix, then you keep this prefix for this activity, the 64 bits. So, and if you want to be traffic analysis hard, difficult to be tracked, then my suggestion is don't change it too frequently because people will know that something is going also wrong there. So you have to, I mean, to make the things that you look like a member of the crowd, we need to understand how the crowd operates. So understand how this crowd is operating in the network. I can be just one member of the crowd, but if I don't know how the crowd operates, it's very difficult to emulate one member. So it's very difficult to answer that question. Depends on which media, depends on which kind of handover policy, depends on a lot of things. But a basic thing is just the right amount of times, not too much and not too little.
Okay.
Yeah.
Another one then. If everyone else can track this data, basically using mobile routers or routers which pick up the signals, can't you just install your own router and track everyone else at the same time?
Oh, that's a quite interesting approach. My way to advocate for a solution to the privacy is that everyone should tupper everyone. I mean, my idea is that it should be open tuppering for the people. If everyone can tupper everyone, if everyone can know where everyone is, you know, they were playing the right role in the war. You know, we should have tuppering devices everywhere. So what happens at the end, you know, we have to. If only a few people can tupper, then, you know, people will have no concerns. But if my students know that I'm tuppering them, my students want privacy. So if everyone is tuppering everyone, the final result is we need a technical solution for this. So I'm in favor of completely open tuppering. Everyone should tupper everyone. You should know where I am. I will try to hide you all the time. You know, but that's the only way. If people do not get scared and it's no media panic with the privacy, no one gives a damn. I promise you that no one gives a damn about privacy, and there's a lot of business based on privacy, and they're not successful because people do not care. But my students care when they feel they are themselves who are monitored. And that sounds like very weird, but that's the only way people understand things. If I know who you are and where you've been yesterday, and which images you have been downloading, probably, you know, that we probably know, and we have in our database, and you know that we know, probably, you know, it will be a big jump into the research, it will be a big jump in the technology. So start to tap all the time and say publicly that you are doing this because of this. So that you have to advocate openly that you do this because of this reason, so you don't go to jail like me. They come to me to the university and say, why are you doing this? Oh, I want to prevent it. So why are you doing this? Because I want to prevent it. It's the only way people understand. The media comes to talk to you, and then you can say the things. So thank you.
I apologize for not having the point for you. I'm always now, but I didn't want to disturb you during the speech.